In this video, we're going to be looking at a relation and determining whether or not it's a linear function, but we're going to be doing this from one of three different types of representations. We need to determine if the function is linear from a graph, from an equation, and, most difficult, from a table. So we're going to start with the most simple and work our way towards the more complex. And when I say we start with the simple, I mean it this time. Let's start with a graph. To determine if a graph is linear, look at it and see if it's a straight line, no changes in directions. If it is a straight line, then it is a linear function. If we stop and think about it for really just a moment, we can understand that that's where these functions get their name. Linear, line, not a coincidence. So as long as it's a straight line, then it is a linear function. So let's take a look at some examples. Here I have four graphs labeled A, B, C, and D. And what I want to know is which ones are linear and which ones are nonlinear. So if I look at graph A, it is a straight line, no change in direction. I'm going to put this under the linear category. If I look at B, notice it's got all these curves on it. It looks almost like a funny shaped M. That is our clue that this is, in fact, a nonlinear function. It has curves in it. If we look at C, it's composed of straight lines, but there is a change in direction right here at the y-axis, so we would say that that one is nonlinear as well. For D, the line is just straight up and down, and it is indeed a line. There's no changing of directions, so we'd say that A and D are linear, they're straight lines, and B and C are not. It really is as simple as that, no trickeration at all. However, in determining whether or not an equation is linear, there are a few more things to remember. An equation is linear if it does not have any of the following. First, it can't have a variable raised to an exponent other than 0 or 1. As long as our variable is raised to a 0 or a 1, it's fine, but no exponents other than that. Nothing squared, cubed, raised to the 4th power, no negative exponents, just zeros or ones, which means in practice you won't see any exponents because we really don't have to write 0 or 1 as exponents. So no exponents. We can't divide by a variable, we can't have a variable as an exponent, and we can't have any operations besides multiplication, division, addition, and subtraction. If we have anything like a square root, absolute value, anything else like that, we know immediately that it is not going to be linear. So let's take a look at some examples. Just like the last one, I just want to classify these as being linear or nonlinear. So let's take a look at A. I don't have any exponents on my variables. That's good. I'm not dividing by any variables. That's good as well. I don't have any operations other than the ones that we would expect: multiplication, division, addition, and subtraction. And so we can very safely say that this is in fact a linear function. For part B, we go through the same checklist. We don't have any exponents, but we are dividing by a variable. We're dividing by x, so we would classify B as being nonlinear. C, y equals x squared minus 6x. Notice here we have a exponent that is other than 0 or 1 on our variable, so we would classify this as being nonlinear. Here we have x divided by 4 minus 1. There are no exponents. We're not dividing by a variable. We don't have any operations other than our basic ones. And so we would say that this is a linear function. Finally, we need to determine if a table is going to be linear. And this is the difficult one. To check and see if a table is a linear function, we have to look at the slope between all the possible points on there. And the slope has to be the same between any 2 points we choose from the table. So let's take a look at it, and really all we're going to be doing is lots of slope calculations over and over and over again. So for each of these, A, B, C, and D, we just need to say if it's linear or nonlinear, which means we need to calculate the slope. So to calculate the slope, we find the change in y plus 5 divided by the change in x, which was plus 10. So our slope between these 2 points is 5 over 10, which simplifies to 1 over 2, but 5 over 10 is fine. And now let's look at these 2 points. 8 to 18, well, we've added 10. 15 to 20, well, we've added 5. 10 divided by 5 is 2. 5 divided by 10 is not equal to 2. So this has a different slope between this point and this point, and this point and this point. Since the slope is not the same everywhere, we would say that A is nonlinear. And then we're just going to repeat this process all the way through. Here we're going from -1 to 0, so we've added 1. Here we've added 1, so our slope is 1 over 1, which is 1. Here we have 0 to 1, we've added 1, 0 to 1, we've added 1. So it's pretty easy to see that our slope is the same between all of those points there, and so B is a linear function. So again, all we're doing is checking to make sure the slope stays constant. Now for some of them that can get difficult. Look at C, there's not an even spacing between the x values, so we'll need to measure pretty carefully. 18 going to 2, we're going down by 16, so the y value went down by 16, and the x value went up by 16. Y divided by x, so the change in y divided by the change in x, gives us a slope of -1. Here, for our second point, we went from 2 to 0, so we went down by 2. This one went up by 2. -2 divided by +2 is -1. And so we see that even though those gaps are different, the slope is still the same. So we would say that this is in fact a linear function. And hopefully you've got the idea. Let's check D. This one goes up by 3, this one goes up by 15. So that would be 3 over 15 for the slope of those points. And you can put that in your calculator and get as a decimal if you are wanting to compare them more easily, or as a simplified fraction. Feel free to do that. That would be good practice. 10 to 11, we've added 1. And 15 to 20, we've added 5. So that is going to be 1 over 5. So the question, is 3 over 15 equal to 1 over 5? And it turns out that it is. The slope is the same there. So D turns out to be linear as well. So the moral of this story is don't count on just appearances for the table to determine whether or not it's linear. You have to actually look at the slope, the rate of change, in between all the points on there and make sure that it stays constant. So again, 3 different representations. For a graph, we just look for a straight line, nice and easy. For an equation, we have several things that we are not allowed to have in a linear function. We're not allowed to have exponents on our variables. We're not allowed to have exponents as variables. We can't divide by a variable, and we have to stick with multiplication, division, addition, and subtraction. Nothing fancy. And then finally, for a table, determine if the rate of change between all the points on the table is the same.